Hey, and welcome back. So today we're just looking at 4.1, Introduction for Reactions. So most of this just deals with being able to understand how to write the reactions and balancing them. So just as a reminder, so here we go, dissolve barium chloride. And here we're also going to talk about the state of matter. So dissolved obviously means it's going to be aqueous. So I have barium chloride. So we know barium, so that's a group 2 reacting with chlorine -1. And so I know that's going to be then BaCl2. Dissolved potassium sulfate. So potassium K plus 1, sulfate, the polyatomic ion, SO4 -2. So that would be then K2SO4. And this is aqueous. This is aqueous because they're both dissolved. Barium sulfate is the precipitate. So precipitate obviously means it's a solid. So I have Ba plus 2, barium and sulfate. So that's going to be then barium sulfate, and that's our solid. And aqueous potassium chloride. So I got potassium chloride. So there we go for that. And that's aqueous. And now we just need to make sure we balance it. So 2 Cl's here. We need to have 2 Cl's over here. There's 2 K's. That gives me 2 K's. Looks like we're all set and hunky-dory. All right, moving on to the second one. Same process. So we got calcium chloride. So calcium chloride reacts with potassium phosphate. So that's going to be potassium's plus 1. And phosphate's a -3, so it'd be K3PO4. And both of those are aqueous and dissolved in water to form the aqueous. So we're going to get the aqueous potassium chloride and calcium phosphate powder. So that's aqueous. And calcium phosphate powder, so that's going to be Ca3PO42. So, and then just go through the process of balancing it. So here's 2 Ca. So I always start with the most complex looking one. So here's 3 Cas. So I'm going to put 3 there. There's 2 PO4s. So let's put 2 there. That's going to give me 6 Ks. So 6 Ks, 6 Cls, 6 Cls. We're done. All right, and C, it says, we know this is going to be our very classic. So here we're just burning stuff. So we're going to burn it in oxygen and going to create carbon dioxide and water. And obviously this is gas, 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 and liquid. And then we could just go through and balance it. So there's 12. So let's put 12, 22 hydrogens. So let's make that 11. That's going to give me 24 oxygens. So it's going to give me 24 oxygens plus another 11. So I need this to be, so there's 11 already. So I just need this group to be 24. So this would be 12. All right, so the solubility rules come in handy here. We're also going to need them later in Unit 7 when we talk about KSP, or equilibrium for solubility. So, but here we go. So the things that are always soluble are going to be your group 1. So everything in group 1. So it's like lithium, sodium, potassium. You're going to have your ammonias. So NH4 plus, your ammonium ions, your nitrate ions, your acetate ions. So C2H3O2 -1. So that's your acetate, and also your perchlorate. So group 1, ammonium, nitrates, acetates, perchlorates. So those are the ones that are always soluble. The ones that are mostly always soluble, we have our halogens, and those have that small exception that if they are mixed with silver, mercury, or lead, so the exceptions make solids. So if it's a halogen with silver, so for instance, AgCl would not dissolve in water because it's a halogen with silver. And then we also have our sulfates are mostly always soluble with the exception of calcium, strontium, barium, and then we have silver, lead, and mercury. So it's technically group 2 and the same one that does for the halogens. Okay, so those are the exceptions. So there's a group 2, and then the same one for the halogens for your sulfates. Those are mostly always soluble. The exceptions make them solids. Other than that, everything else would be soluble in water. All right, so here for A, it says calculate the moles of O2 that is released. So what you're really looking at is we're going to heat up, it says we're heating this metal and then it loses. So obviously the loss in mass has to be from the O2. So this loss in mass, if I subtract these out, we get the O2 loss in mass was 0.107 grams. So we just need to convert that to moles by dividing by 32 grams per mole, and we get 0.00334 moles of O2 that is released. All right, so here for part B, it says the amount of metal present in the crucible is equal to this many moles. So what we really want to do is figure out, so in order to do molar mass, we know molar mass is going to be grams divided by moles. So what we need to figure out, so we know the moles of the metal, we just need to figure out the grams of the metal. Well, we can take and figure out, well, what's this loss difference, because that's just simply the metal there, because all of the oxygen is gone. So if I take the 25.940 and subtract that out, that tells me that I have 1.444 grams of just the metal. If I divide that out by the 0.0134 grams per mole, we get a molar mass of about 107.76, which is approximately 108. So in order to figure out the identity of this metal, we just need to figure out what has a molar mass of around 108 grams per mole. So we're looking for something around 108. So it looks like 107.87. That's the closest. So our mass must be silver. So therefore, I know that this is elemental silver with a molar mass of about 108. So that's it for part B. All right, so for part C, we're looking for an empirical formula. So I want to know what is the moles of Ag and what is the moles of just O in order to divide by the smallest and get their ratio of their moles. So this one we knew Ag was 0.0134 moles, and we knew O2 was 0.0334, but that's for O2, and we know that there's 2 oxygens for every one of the O2s, so therefore for oxygen it'd be 0.00668 moles. And now I can divide both of them by the smallest to create the ratio, and that tells me that this is approximately 2, so therefore my empirical formula must be Ag2O. And that makes sense because Ag is typically +1 minus 2. So there we go. There's that for that. So now we can do our formula. So I got Ag2O going to Ag plus O2. So balance that out. We know we got to have 2 of these and 4 of those. So that would be our balanced equation for that experiment. It says, is the process represented by the equation above classified as a physical change or a chemical change? Well, obviously it's a chemical change because we are changing the physical composition of the product. right? So we're changing it from silver oxide to silver and oxygen, so breaking it apart. So decomposition is going to be a physical process, I mean a chemical process. All right, the last couple here. So it says we got aqueous solutions of ammonium sulfate. So I have ammonium sulfate, barium nitrate, and we're going to get something. So we know the barium is going to mix with the sulfate, so that's +2, -2. So we're going to get barium sulfate and ammonium nitrate. And now that's so we need to put in our state of matter. So we know this is aqueous, because it says they're aqueous. We just need to figure out what are these. Well, we know ammoniums and nitrates both are always soluble, so those are aqueous, and therefore if we're getting some from a precipitate, we're getting this as obviously our solid. So that's our balanced equation. So it would be, and then we just need to balance it. So let's see, 2 ammoniums, and that would balance the whole thing. Overall ionic equation, that's just writing them all out as ions. So in other words, it would be 2 ammonium ions, 1 sulfate ion, 1 barium ion, 2 nitrate ions. And then the solids don't become ions, they just stay together as solids. And then we have 2 ammonium ions and 2 nitrate ions, and so forth and so on. Now, when we're talking about spectator, we're talking about the things that can cancel. So what we're looking at here is what does not, so what is not part of the solid. So what are the ions that are not part of the solid? So I can see ammonium and nitrates. They're exactly the same on the other side. They would cancel. So therefore, my ammonium ions and my nitrate ions are both spectators. And the net ionic is going to just be the stuff that we did not cancel. So if I was to cancel this and this and this and this, that would be our net ionic reaction. And I'm just going to write it in the same order. Barium +2 plus sulfate -2 becomes barium sulfate solid. And that would be how you do the net ionic equation. And that is the end. I'll let you guys let you try the last one. So try that out. Pause it. Try it. I'll put the answer. And there's what your final answer should be. And that is all. That was the last part of the little summer work or summer prep work to get us started for the beginning of the year. See you guys in a couple of weeks. Looking forward to it. A fantastic and fabulous year. Later.